Okay, looks like we're live. Okay. Hello, everyone. I'm Samir, a freshman at MIT, and I'm helping to organize the HMMT education event. We're so happy you could join us today with Hahn Lheem teaching about different areas of math. I'd like to begin by sharing a couple logistical ground rules. Feel free to use the Q&A feature to ask any questions. So if you have a question, use the Q&A feature, not the chat. And you can also upvote questions that you think are interesting. However, I'd like to remind you that Han is taking time out of his own day to join us, which we're very grateful for. So be on your best behavior and respect the teacher, the classroom, and your peers. We will remove you if you're being disruptive in the chat or the Q&A, so don't abuse the ability to ask questions. Now I'll introduce Han. Han is an intended sophomore, currently on leave from Harvard University. He was an avid math competitor in middle and high school, whose excitement towards math is only sustained in college, especially once he realized just how much math exists beyond the 4 subjects tested in most math contests. He enjoys teaching math and hopes to continue spreading mathematical opportunities to everyone. And with that, I'll pass it off to Han. And yeah.
Yeah, thanks so much, Samir. It's really great to be here, and I taught for the first education session, which happened right after the February tournament, like earlier this year, and that was in person. And although we can't be in person today, I'm still really fortunate to be able to have this opportunity. So thank you all so much for spending your Sunday to actually listen to some math. I think this is a very valiant thing to do, and I really appreciate the interest that you guys have. Okay, so today I'm going to give you a talk that I wish I kind of had when I was in high school. As Samir kind of mentioned in that wonderful introduction, I did math contests in high school, but I didn't really realize how much math existed beyond math contests. And I knew some things like, maybe I heard some names floating around, but I never really knew what they were until I got into college. And then I saw just the course catalog, and it just blew me away at how many different things I had never even heard before. And so although we only have around like 45 minutes together, I'm going to try to do my best to touch upon some really interesting topics in math that hopefully, later on you could explore more in depth. So this is what is math like in college? I put at most 9 topics because I don't know if I'll get through all of them, but I'll do my best. And without further ado, let's get started. So before I go into any math, I'm going to start off with some opening remarks on how I like to approach mathematics in general. So I like to think of mathematics as a language. After all, half of what we do in mathematics is just taking some concepts in math and finding correct language to express these notions. And in particular, I think mathematics is a specific way of communicating certain ideas. I want to go off on this analogy between mathematics and language a little bit more by saying 2 things. First, if you maybe lived in the United States for the past 5 years, or you've listened to world news, then you may have heard this phrase that's thrown around a lot: fake news. Right. And it's because maybe 5 years ago, there's a certain presidential candidate who was like, oh, well, I think that the media is really representing me very incorrectly. And so I want to put a label to this notion that the news is representing me not fairly. And so he kept using this term fake news. And because he kept using it out of necessity, now it's a very common phrase in our vocabulary. Just like with language, in math, if you ever see a definition and you don't really know where it comes from, it probably comes from something pretty important that comes up enough such that mathematicians realized, oh, we should probably put a name to this so we don't have to refer to this as some random idea over and over again. The second analogy is that, well, I'm Korean. Unfortunately, I'm not the best at speaking Korean. So maybe if I have a sentence in Korean and I want to translate it into English, which I know a lot better than Korean, then I can use some translating device like Google Translate in order to translate into English. By the way, I agree with Google Translate. Likewise in math, we have some subjects in math that we don't really understand too well, but we also have areas in math that we understand a lot. So one of the goals in math is to try to take the things that we don't understand and putting them into a language in terms of the things that we do understand really well. I'll give concrete examples of this at least 2 times during this talk, so just look out for that. Final thing is I will be covering a lot of things, maybe like 2 years, 3 years, even 4 years for some people of undergrad math. So I'm going to be skipping over a lot of details. So I definitely encourage you to study these as you move forward, but hopefully this just gives you a taste of what math might be like in college. Okay, now let's get to some math, and let's focus on our first 2 topics out of 9. I'm going to call these under the branch of AP Calculus. But okay, let's not jump the gun here. Let's start with AP Calculus. So in AP Calculus, if you've taken it before, then you may have learned how to do things like take limits, tell when a series converges or not, like this geometric series. Find derivatives. For people who haven't taken calculus, you look at a graph and you take a point and you see what is the slope of the line at that point. You can also evaluate integrals. If you take a curve, then you can find the area underneath that curve. Well, let's take a step back and think about these notions again. If I ask you something like, what is the limit as x approaches a, you might say, well, if you look at a graph and you see the value as you approach a, that's your limit. But what does it mean for something to approach something else? What does approach mean mathematically? It's a very literal term, not a mathematical term. What if I ask you, when is the function continuous? What is a continuous function? You might say, oh, if you draw the graph for it, then I never have to pick up my pencil. Well, a lot of graphs go to infinity. So if you keep drawing to infinity, which you can't really do, how can you tell that you never pick up your pencil at any point? When does a series converge? I might ask that question. Again, you might give some vague answer like the sum gets closer to a certain value as you keep adding terms. Well, again, what does it mean for something to get closer to a value? So you see that in AP Calculus that you play around with a lot of these notions, and maybe at best you learn how to calculate these notions without actually knowing what you're calculating. So you're playing around with a lot of vague notions floating up in the air. And so our first topic that we want to address is, well, how can we define these things better? Here is AP Calculus, which is more commonly called real analysis. So I want to first note that in AP Calculus, all the functions that we deal with are a very specific type of function called real functions, where we put in a real number and the output is another real number. Well, what exactly are the real numbers though? If I give you a real number, then maybe you can tell me if it's real or not. But as a collective set, what properties does it have? How can we differentiate the set of real numbers from, say, the set of rational numbers? I won't go into the details for this because this requires some time, but this is how I see real analysis is structured. First, we need to actually define what the real numbers are. Once we do that, then since we have a working definition of the real numbers, you can start developing everything that we learned from AP Calculus, like what is the limit, what is a continuous function, how to take derivatives. We can do that a lot more rigorously using our definition of the real numbers. I must admit that some of these can get a bit messy. Maybe you've seen something like epsilon delta definitions for limits, and they look like this. And so these are some of the definitions you might see in real analysis. It's not pretty. You have a lot of variables and it's a lot of symbols going on, but I would say although it can get a bit tedious at times, it is pretty important because we want to take these things from AP Calculus and be able to express them a lot more concisely. Well, let's go into something more interesting. And before I do that, I want to rant a little bit more about real functions because sometimes they can get pretty messy. Here's one example. Here's something called the Weierstrass function. Here's a diagram for it. This is like the general shape of the Weierstrass function. The very weird thing about this is that it is continuous everywhere. Continuous everywhere. It is differentiable nowhere. If you take any point, then you can't find a tangent line at that point. It's differentiable nowhere, which is really weird, and it breaks so much intuition that we have about real functions, about AP Calculus. So real functions can be a bit messy. Real numbers are not nice. But what are nice are complex numbers. So let's look at complex functions. This is the heart of AP Calculus, or something's called complex analysis. Complex functions are very nice. And before I move on, I'm going to change one word. So I'm going to call here holomorphic functions are differentiable functions in just the complex numbers. Okay, and you can already see that holomorphic functions are a lot nicer than differentiable functions because holomorphic sounds cooler than differentiable, right? Like, holomorphic kind of sounds like hologram, and you see like Star Wars figures like holograms. Anyways, yeah, so holomorphic, but beyond just the name itself, holomorphic functions are really cool because they satisfy properties that would never happen in real analysis. And as like my professor in freshman year said, this is when he realized that we're not in Kansas anymore. So first thing, if you can differentiate a holomorphic function once, you can take the derivative once, you can take it infinitely many number of times. That's crazy. That means that basically any differentiable function is basically just an infinite polynomial, or maybe just a finite polynomial, which are arguably like some of the best functions you can deal with. Second thing, if I define a function on the entirety of the contiguous United States, right, on the contiguous United States, and then I define a function on just one penny on the ground, just one small penny on the ground, just by telling you the values of the function on that one penny, you can tell me the value of the function anywhere in the United States, which is crazy. Comparing a penny to the United States, this is absolutely wild. And these are just two of the really nice properties of complex functions. Well, because they're so nice, you can do a lot of things in complex analysis that we can't do in real analysis. For example, you might come across integrals like this, where you don't know how to actually compute them using AP calculus techniques. Well, if you think of these real functions as just complex functions, just restricted to the real numbers, then you can use complex analysis tools to actually evaluate integrals like these. And so you can do a lot more things with complex analysis, and I think it's one of the coolest parts of analysis out there. Yeah. Okay, this is done with analysis. Now let's move on to our third topic, which is something you're probably very familiar with, number theory. So number theory, you probably have some experience with it from contest math. Maybe you learn modular arithmetic, right? If you multiply 3 by 5, take the remainder, and when you divide by 7, you get 1. So we say 3 times 5 is congruent to 1, mod 7. You might also know results like Fermat's theorem, which are extremely nice, right? And you might also have come across divisibility rules. When can we tell if a number is divisible by 9? Or if we divide by 9, then what is the remainder? Well, what do all of these kind of encapsulate? What are all of these related to? What is the study of number theory? Well, the essence of number theory, I would say, is just the study of perhaps the most basic thing we can talk about in math, the integers. And in case you don't know what the integers are, I've put 7 of them here. Well, just like with real analysis, right? It's kind of difficult for us to define the real numbers. We don't exactly know what they mean. Well, for here, it's kind of hard for us to actually understand what the integers are. For example, why is it that between any two consecutive integers, it's just 1, which is, by the way, the number where when you multiply anything to 1, it just stays that same number. Why is the difference between two consecutive integers 1? Another way to frame this question is, if we take only all the even integers, the set of even integers, what is the difference between the set of even integers and just the integers? How can we tell the difference? What are the properties that distinguish the integers from some other sets? In order to answer these questions, we need to actually start by defining what the integers are. What exactly are the integers? Again, with real analysis, like how I didn't really answer this question for the real numbers, I won't answer this question for the integers, but I'll try to address this question in a roundabout way. And to do that, let's look at chemistry. So in chemistry, at least to my understanding, because I haven't taken a chem class in quite some time, but for chemistry, you study compounds and molecules, right? But compounds and molecules are made up of atoms and elements. So if you want to study compounds and molecules, you got to study their building blocks. You got to study their elements. And while chemistry does a fascinating job in showing, the elements organized in this fashion and being able to categorize them and putting specific properties to each element. Can we do something similar with number theory? Well, let's look at the integers. How can we decompose the integers? Well, we can prime factorize every integer into primes, right? So maybe for chemistry, if we want to study atoms, for number theory, we should study the prime numbers. And so let's do that. So there's some really big questions regarding prime numbers that are central focus to a lot of things in number theory. I'll give you some of them. The first has been answered for quite a long time, which is how many prime numbers are there? There's a really fascinating proof by Euclid. If you don't know it, then you should check it out. It's really simple and really easy to understand, but there are infinitely many number of primes. Really, the question is, how many prime numbers are there less than n? This is very similar, right? But this is actually a lot harder to answer. We'll investigate this shortly. How many prime numbers are there 1 mod 3? Or in general, how many prime numbers are there a modulo m? This is another really interesting question. And there's some other questions too that we can ask, that have been studied a lot in number theory, and a lot of them are actually still unsolved, which means that we have a lot to still discover about prime numbers, but these are very relevant questions in math. Well, in number theory alone, we don't have too many tools to answer these questions straight up. However, just like with Korean, I might not be able to translate Korean sentences on my own, but if I translate them into English, then I can understand what they mean. Well, in order to answer these questions about primes, maybe instead of just looking into number theory, we can borrow techniques from other topics and use that to translate these questions into some other mathematical language. Well, the only thing we talked about so far is analysis. So let's use analysis to answer these questions. Here is the birth of our fourth topic, analytic number theory. Well, to talk about this, let's first go back to something from AP Calculus. Let's talk about the harmonic series. This is the sum of the reciprocals of all the integers, as you can see here. Well, you might remember from AP Calculus, or you might know the proof of this, but this diverges. It goes to infinity. And here's a quick proof for the people who don't believe me. Okay, well, this diverges. That's not too fun, right? We don't have a specific value, and we want to be able to actually calculate some things. So I'm going to be a bit optimistic, and I'm going to change one small thing. What if instead taking the reciprocals of the integers, we square the integers first, and then we take the reciprocals? If we sum all of those up, what do we get? Here's where analysis comes into play. I won't go through the whole proof because we don't have the time for that. But basically, what you can do is you can use analysis, take the Taylor series of sine of x, and by doing some manipulations, you can get this very famous result that the sum of the reciprocals of the squares is equal to pi squared over 6, which is absolutely remarkable. Pi is a very geometric number, right? It's when you take the circumference of a circle divided by the diameter. And so now you have this very unrelated series that talks about the reciprocals of the squares, and then they sum up to not just pi, but pi squared, and then you divide it by 6. So I think this is a very fascinating result, and it's quite remarkable. Even though it's so fascinating, though, I'm not satisfied yet. I want to keep going on. What if we replace the exponent 2 with any integer? Even better yet, what if we replace the exponent 2 with any real number? Or even better, because we actually have stuff in complex analysis, what if we replace the number 2 with any complex number? Let's do that. Let's generalize this problem. Let's replace the exponent 2 with any complex number. What do we get? This is what we call the Riemann zeta function. That Greek symbol at the beginning is zeta. It's fun to write. So zeta of s is equal to 1 plus 1 over 2 to the s plus 1 over 3 to the s plus blah, blah, blah. From the work that we just did, from the result that I just showed you, we know that if we plug in s equals 2, then we get zeta of s is equal to pi squared over 6. This zeta function, I can't talk too much about it because that requires going a lot in depth into other parts of number theory, but I will say that it has very remarkable implications in math. You might recognize the name Riemann from two places possibly. One, Riemann integrals, and second, the Riemann hypothesis. And the Riemann hypothesis is actually just a statement about the zeros of the zeta function. Where is zeta of s equal to 0? This is an unsolved problem. We haven't been able to prove it yet, but a lot of math papers actually assume that this hypothesis is true. And because of that, if we are able to prove this hypothesis, it has very, very significant consequences in so many areas of number theory. In fact, it's so important that it was called one of the millennium problems at the beginning of the century. And if you prove it, you can win $1 million. That's some bank right there. I will say, though, that this is probably not the best way to win $1 million. There are definitely other better ways to do it. But at the same time, if you do prove it, then you can get infinite mathematical clout in the rest of history. So maybe if you have some free time, you can try your luck and see what happens. Okay, well, I can't talk too much about the Riemann hypothesis specifically because, again, it's very involved and it involves a lot of complicated things. But I want to talk about some of the questions that I posed earlier about number theory. So let's talk about the distribution of primes. And this will tie into some of the things with the Riemann hypothesis and stuff like that. So our first question is, how many primes are there less than n? Remember, that was one of our questions. Well, we have a result that tells us roughly the answer. This is called the prime number theorem. And you can tell it's really important because it literally has the name prime number in it. So let pi of n be the prime counting function, i.e. the number of primes less than or equal to n. Then we say pi of n is asymptotic to n over log n. Now, asymptotic just means that if we take the ratio of pi of n to n over log n, the ratio goes to 1 as n goes to infinity. It approaches 1. As a quick corollary, if you divide n over log n by n, you're going to get 1 over log n. So the probability that if you choose a random integer less than n, the probability that that's prime is around 1 over log n. And here's a test with 2021. You see that the difference, the error term, is around 1 over 50, which is actually not too bad, considering how primes have very wonky patterns. Here's a visual representation of what's going on. So if we divide pi of n by n over log n, that gives you the function at the top, the blue graph. You see that it kind of approaches 1 slowly, but it surely approaches 1, which is all we care about. It goes towards 1 as x goes to infinity. You might notice, though, that the bottom graph actually does a lot better. It goes to 1 a lot faster than the top graph. And so we actually have a stronger version of the prime number theorem. But in order to specify the error term for that, we actually need the Riemann hypothesis. So this is what it says. Pi of n is equal to that wonky integral plus this error term. Big O just means that it's bounded by the function in the argument. So the error term is bounded by square root of n log n, which if you've taken computer science or you're familiar with big O notation, this is not too bad of an error bound, considering, again, how wonky primes can be. And that error bound only is based on us assuming the Riemann hypothesis. If we don't assume the hypothesis, then the error term that we know so far is really messy. Okay, cool. Our second result from analytic number theory is called Dirichlet's theorem. And this says, this addresses the question from earlier on how many primes are there 1 mod 3. Well, this says that there are infinitely many primes. So let's see this as an example. If we take the infinite arithmetic sequence that starts with 1, and the common difference is 3, like I've given the first few terms over here, there's going to be infinitely many primes in this infinite arithmetic sequence. And if we start with any number a and take the common difference as n, where n and a are relatively prime, then that infinite arithmetic sequence will have infinitely many primes. Yeah, we can do actually even better than this. So we know there are infinitely many primes 1 mod 3 and 2 mod 3. But how many of them are 1 mod 3? How many of them are 2 mod 3? What's the ratio between them? Turns out that if you take the congruence classes, the primes are evenly divided. They're evenly distributed. As an example, if you take the primes greater than 5, right, then we know that all primes must end in 1, 3, 7, or 9. Those are like the 4 columns you see here. If it ends in 5, then the number is going to be divisible by 5. If it ends in an even number, it's going to be divisible by an even number. We've shown that if you take the density of the primes, then 1/4 of all the primes will be ending in 1. 1/4 of all the primes will end in 7. 1/4 of all primes will end in 3. 1/4 of all primes will end in 9. So this is quite remarkable. Yeah. Okay. In order to just save time, I'm going to move on. And our next topic is going to be Galois theory, topic number 5. Before I start, I'm going to give some brief background of history here. So there's a man named French dude named Évariste Galois, or Évariste Galois, if you want to be French. I'm not French, so I did not pronounce that too well. Galois was a very passionate man. He was passionate in math. He was passionate in politics. Some say he was also passionate in romance as well. When Galois was 18, he developed basically all the things that I'm going to talk about for Galois theory. He kind of wrote them in a very obscure way, and people didn't really pay attention. He submitted it to journals, and they were rejected because they had lots of complaints about it. Only 10 years later, though, 10 years after he was 18, did someone actually realize that, oh, these are actually really important, and then it became, the rest is history. Unfortunately, though, because he was politically active, he got in a duel with this one man when he was 20, and he unfortunately got shot, and he died at that young age. So a lot of times I wonder, if Galois lived past 20, how much more of his name we would see in math. But I think the better moral of the story here is, number one, don't get into duels. And number two, if you can do all this stuff at 18, then you can do a lot of stuff in your future. So be hopeful. Okay, but what is Galois theory? Well, let's go through some quick exercises. Let's solve for x. If I give you a linear equation, well, this is pretty easy. X is minus b over a, right? What about quadratic equation? Again, pretty easy. Hahn, I went to middle school. I know what this is. This is quadratic equation. All right, quadratic formula, sorry. Okay, what if I ask you to find the root of a cubic equation? Can you do this? Turns out that you actually can. Here's the formula. I took the pains to type it out, but just note, if you find yourself trying to memorize this, then you should probably check yourself. Don't memorize this. The important thing, though, is that this formula exists for cubic equations. What's more is that if you look at all three formulas so far, they only use 5 things. They use the 4 basic operations: addition, subtraction, multiplication, division, and you can take nth roots. So for quadratic, you could take square roots. Over here, we see we can take cube roots. Okay, this is pretty nice. Let's go one step further. Is there a formula using only these 5 operations? This is our condition to find the roots of a degree 4 of any quartic polynomial. Is there such a formula? Turns out that there actually is. It's way too long for me to put here, but the important thing is it exists. Here's our next question. Is there such a formula for degree 5 for quintic polynomials? The answer here, no. For some reason at 5, the pattern suddenly breaks. And you might ask the very naive and obvious question, why? Why suddenly at 5 does this formula break? Why does the pattern break at 5? What is so special about the number 5? Well, I can't tell you the answer because that's the entirety of Galois theory, but I will say something pretty vague. So I apologize in advance. But what happens is if you look at the roots of the quintic polynomial, and you basically look at the permutations of those roots, if you find the symmetries of those 5 roots, then those permutations have a certain structure that you don't see for degree 4 polynomials, that you don't see for degree 3 polynomials. Well, this is kind of vague, as I said. Permutations, symmetries. How do we really study permutations? How do we study these symmetries? Where do these come from? Welcome to topic number 6, group theory. So let's start with permutations because that's where we just ended off of. So we can note that if we start with a set like 1, 2, 3, 4, 5, what we can do is we can arrange them in any possible way that we want. In other words, we can encode all possible symmetries of the set through permutations. I give you one permutation or one rearrangement right here, but you can do this in any other way. Another important thing to note is that if I give you a permutation, there's a way to reverse that action of that permutation. So we can be like, oops, we made a mistake. Let's go back to the original. Every permutation has an inverse. So given the green permutation, you can reverse it with the red. Permutations don't only have to act on sets, though. We don't always need to do permutations on 1, 2, 3, 4, 5. We can do them on other things. Let's look at a triangle, for example. Let's start with a triangle, and let's label the vertices A, B, C. Let's permute the vertices of the triangle by relabeling the vertices. Well, triangles have a certain condition that there are only finitely many ways for us to find the symmetries of a geometric object. So over here, we're going to restrict ourselves to rotations. So we rotate the triangle, or we reflect the triangle. We can reflect them along some axis. Let's first try rotation. So let's rotate it 120 degrees counterclockwise. This gives us this. A goes to B, B goes to C, and C goes to A. Okay. What if we flip it this time? So I call this flip A because A used to be at the top. So we're going to refer to our original triangle. We're going to flip along the axis that goes down the middle. I call this flip A, or for consistency, FA. What happens if we do this flip? Well, C stays the same, and A and B, they swap places. Okay, this is cool. So we see that we can do rotations and flips. Is there a way, though, for us to go from our very first triangle to our very last triangle in just one take, just one go? Can we do that? Well, if you think about it for a bit and you notice some things, you see that B stays the same and A and C swap. So maybe if we take the axis that goes through B and we flip it along that, then we can get our last triangle. So I'm going to call this flip B, or in other terms, F of B. And we see something really beautiful going on here. We see that we can take a symmetry, some action on the triangle, and another action on the triangle, and combine them to get another form of symmetry. So here we call this composition. So we can compose 2 actions together. F of B is F of A composed R120. And these encapsulate the symmetries of the triangle. Permutations don't only need to act on triangles, though. They can also act on other things. So you have symmetries in basically everywhere, like not just in math, but everywhere in the world. Even the integers have a lot of symmetry. If I add 3 to the set, it's still going to look the same. All we're doing is just shifting everything by 3. So that's our symmetry here. We're just shifting the set. If we take the integers mod 7, we put them in a circle. If we add 3, we're just rotating, or I guess my mirror is flipped. So rotating the circle by 3 ticks, by 3 units. And in fact, group theory is really prominent in physics and chemistry, among like other subjects. I was really surprised in college by like how many group theory classes physicists need to take if they need to understand stuff like quantum field theory. And for chemistry, if you consider something like, I don't know, a tetrahedral bipyramidal structure, I barely remember what that is, but that only has finitely many number of symmetries. And by understanding those symmetries, we can understand how they connect with other types of structures. And so group theory is really common in a lot of areas of STEM. Well, what is actually a group though? Well, let's look at the symmetries of a triangle. I put them here in terms of symbols, but R is rotation, F is flip. And identity is ID, so you just keep it there. You don't do anything. These are all actions, right? We act on a triangle. What if we think of them instead of actions as just abstract elements? They're just elements of a set. And we have some way of combining two elements together, kind of like addition, some operation that combines two elements together to get another element. This is essentially a group. A group, first and foremost, is a set. It's just a set, but it represents the symmetries of some kind of object. And I'm going to put two more specifics here. This isn't the exact definition of a group, but it's good enough for our purposes. First, we have a way of combining two actions together. I can rotate something and then flip something, and that's another flip, right? Every action is also reversible. I can reverse every action. For permutations, we could reverse every permutation. If I flip the triangle, I can flip it again along the same axis to go back to the original, right? So these are two conditions that a group must satisfy. Here are some examples of groups that we've been through, that we've covered already. I want to make one small notation change. So I'm going to call the symmetries of a triangle as D6 and the set of permutations as Sn. So if there are 3 elements, it's S3. For 5 elements, it's S5. These are like the third and fourth groups right here. Okay, well, here's one interesting notion involving groups. So we might call two groups as different things. They also might have different elements. You know, we might have different labels for their elements. But what if two groups can still encapsulate the same type of symmetry? Here's an example. Let's start with the triangle again, right? This is just the group D6, the symmetries of a triangle. Here's one. Here's just the identity where we keep the triangle as itself. And then I'm gonna put the vertices into a set, so ABC like this. We can do any of these symmetries, right? We can rotate it, we can flip it, and this gives us a unique permutation on the vertices, right? Like such. And we put them all into a list though. We see that on the left, we have all the symmetries of the triangle, and on the right, we have all the symmetries or all the permutations on the 3 vertices. Turns out that they look exactly the same. And furthermore, if we combine 2 of the elements on the left and the corresponding elements on the right, their output is still corresponding. So they basically have the same certain structure. They have the same symmetries and they have the same structures. So they're basically the same. We just call them different things. So what we call these two groups are the same, or since we're pretentious in group theory, we call them isomorphic. And just as an analogy, you know, for geometry, we say triangles are congruent. For groups, we say they are isomorphic. Okay, so this is very important. We have this notion that two groups are the same. It'd be really nice for group theory if we could understand all groups, right? For chemistry, we understand like basically all elements. So what if we could do the same thing for groups? Can we classify all groups? I'm going to be a bit more specific because we said that, you know, two groups might be called different things, but they're still the same. So can we classify all groups up to isomorphism? Well, turns out for finite groups, we actually do a really good job. I won't go into specific details, but for finite groups, we have a lot of tools to basically determine if you give me the number of elements in the group, then I can probably give you like some finite number of possibilities that the group could be. It is really powerful. But maybe you want to do a little bit better than this. Okay, so let's look again into analogy with chemistry. So looking at the periodic table, we remember that if you want to study chemistry, you've got to look at the atoms, at the elements. For number theory, to understand the integers, you've got to look at primes. So can we approach group theory by studying the building blocks of groups? What are these building blocks? Well, the building blocks for group theory, we're going to call simple groups. And so here's our revised question. Can we classify all simple groups up to isomorphism? Can we classify all simple groups? This is where things get really interesting. This is basically like, think of revised periodic table for group theory, but a lot cooler. So just like you have halogens and noble gases as like families, you also have families here. First, you start off with 3 general families. I won't describe them, but you have 3 general families to start off with. After that, though, what happens is you have 26 random groups that are not in any family. You have 26 random groups, which you call sporadic. Here are two of the largest ones. The second largest one is called the baby monster group. Baby monster group. This has around 4 times 10 to the 33 number of elements, which is massive. The largest group you might have guessed is called the monster group, which is around 8 times 10 to the 53 elements. It contains this many number of elements. That's around the number of atoms in Jupiter. So it's an exorbitantly massive number. What's even funnier is that this monster group actually contains 19 other groups. And so if you combine these 19 groups plus the monster group, that gives you 20 groups. And these 20 groups, we call them the happy family. And this is like as cute as math can get, right? Happy family. That's so wholesome. Kind of like the HMMO organizing team. Okay, anyways, so yeah, I think this is like one of the best parts of mathematicians are usually bad at naming stuff, but here I think they got a spot on. Okay, well, we've talked a lot of things about, abstract structures and such, but let's talk a little bit more about less abstract things. So let's go into something more geometrically related. Here is topology. We're nearing the end here. So for our purposes, we're going to talk about the study of surfaces. The study of surfaces for our purposes. I'm a poet and I know it. I say for our purposes because some topological spaces aren't related to geometry, but for the most part, we only care about things related to geometry. You might have heard the joke that like, ha ha ha, topologists are so dumb, they can't tell the difference between a coffee mug and a donut. Well, here's why we might not be able to tell the difference. If you take a coffee mug, right, on the right, and then you fill up the coffee mug, then you can you first fill it up, and then you kind of stretch it out, and then you form a donut. Right? Here's another visual to kind of convince you that this is true. Well, okay, well, this is pretty cool. And now we see that there's almost like with isomorphism, we have this notion that two surfaces, that two shapes can be the same thing. All you have to do is just continuously move from one to the other without like breaking anything, without cutting anything, without making any holes, very tamely just continuously turn one into the other. What we call this is that we say that coffee mug and a donut are the same, but in math, since we're pretentious, we don't call them the same, we call them homeomorphic. So in topology, our notion of sameness is going to be called homeomorphic. Okay, here are some examples of homeomorphisms. So the letter A is homeomorphic to the letter O. Okay, you can kind of convince yourself this is true. A square is homeomorphic to a circle. You can think of the square as kind of made of Play-Doh, and you can kind of like round the corners of the Play-Doh to form a circle. Okay. Some other interesting homeomorphisms are you can take a plane and you can take a sphere, but you remove one point. So over here, I remove the point at the top. And what you can do is basically think of it as like you start from the opening at the top and kind of like stretch out, unwrap the sphere and like flatten out. Then you kind of get the plane. You can also like more mathematically rigorous way to do this is you can take a stereographic projection. I don't have a diagram, unfortunately, but you can search it up. And I think the notion is pretty cool. So we're able to tell if two spaces are homeomorphic by considering them and kind of visualizing them. But what if you can't visualize them? What if I give you a sphere in 1000 dimensions and a sphere in 2020 dimensions? How can we tell the difference between those two spheres? It's really hard. We can't really visualize anything beyond, I don't know, like 3 dimensions. And even with 3 dimensions, what if we have spheres, what if we have surfaces that we can't really embed into 3 dimensions? Take like the Klein bottle and the real projective plane. How can we tell that these two things are homeomorphic? So our big question right now, our big question for topology is, how can we tell two surfaces apart? Or in more mathematical terms, how can we tell when two surfaces are not homeomorphic? Well, okay, this is a big question. And unfortunately, in topology alone, we can't answer them with just tools in topology. But we've encountered this problem before, right? In number theory, we couldn't answer those questions about primes with number theory alone, so we borrowed stuff from other places. Likewise, for here in topology, since we can't do stuff in topology alone, we want to translate stuff from topology into something else that we actually understand better. Like with Korean, I want to translate something Korean to something English. For here, Korean is like my topology. I want to translate something to topology into something else. So what do we understand a lot in math? Well, I would say two things. One, the first thing that we understand the best is linear algebra. The second thing that we understand the best is arguably group theory, abstract algebra. And so if we can change topology into a question in group theory, that would be really nice because we have a lot of tools in group theory. So here's our big question now. How can we translate from topology to group theory? How can we take some topological space like a coffee mug or a torus or just any plane and turn that into a group, an abstract algebraic structure? How do we make that translation? Well, group theory is about like abstract algebra, and we're using that for topology. So here is our second to last topic, algebraic topology. Unfortunately for this, I might be like very hand wavy. I might just like wave my hands and be like, okay, this is my explanation. But just bear with me here. So the condition for homeomorphism is very strong, as we've like seen before. It's very specific. So what we're going to do is we're going to kind of settle for something a bit weaker. We're going to say, we're going to start with a homeomorphism, right? And then what we're going to do, we're going to allow for collapsing. We're going to allow for us to contract spaces into smaller spaces. What we call this is homotopies, or we say that two spaces are homotopic equivalent. For example, we can take the entire plane, and just squeeze it down into one point. We can take this two-dimensional thing and squeeze it down into 0 dimensions. The plane and the point are homotopic. If you take the Mobius strip, if you look at the red boundary on the outside, what we can do is all the points on the boundary, we can kind of compress them, squeeze them onto the band in the middle, and that just forms a circle. So by doing that collapsing, we say that the Mobius strip is homotopic to a circle. Here's where the group theory comes into play. The really fascinating thing that we've been able to do, which is really crazy, is that we start with two topological spaces, X and Y. Let's say that they're homotopic, okay? What we've been able to do is we're able to construct out of these topological spaces, we're able to make a group. I won't explain the process, but it exists. And if you're really interested, you can like search it up on your own. I'll give the name soon. Turns out that if X and Y are homotopic, if they're equivalent in this manner, then the groups that they produce are also equivalent. They're isomorphic. They're equal to each other. What we call this, we use pi1. So pi1 of X is a group produced by X. Pi1 of Y is the group produced by Y. We call this the fundamental group, which makes sense because it's like the first group, pi1. Well, why is it called pi1? Why is there the 1? Well, it turns out you can do more than just to find a fundamental group. There are also ways for us to not only take pi1, but make a process so that we can make another group, which we call pi2. And it turns out pi2 of X and pi2 of Y, they must also be the same if X and Y are homotopic. We can do this again, pi3, keep on going. And for all of these pi n's, these larger groups, they still must be equivalent to each other if X and Y are homotopic. We call these the higher homotopy groups of X. And so instead of trying to see if two spaces are homotopic, what we can do is first compute their groups, their corresponding groups. And then if those groups don't match up, then X and Y cannot be a homotopic. So this becomes entirely a problem in algebra now. I'll stop this conversation about algebraic topology here. There are other ways to construct groups from topological spaces, but they're a bit hard to talk about, so I'll just push that conversation for a side. Okay, the last thing I'm going to do, I'm a bit running out of time here, but the last thing I'll do is something related to category theory. So this is our final finale. We've reached the end. Here it is, the end game. So we've talked a lot about like a lot of different structures today, a lot of different mathematical objects. So we start with sets, right? They're probably like the most basic things. If you study some linear algebra, you may know something called vector spaces, which are, again, just some other object. You also know groups. We know topological spaces. These actually share certain properties together. What we can do, in fact, is you can take one set and map it to another set. We can take one vector space and map it to another vector space. There is a way to go from one of these objects to another of the same object. We call them different things, right? For sets, we call them functions. For vector spaces, we call them linear maps, which we represent as matrices. For groups, the isomorphic property is actually a very specific property. If we want to generalize it, then we call them homomorphisms. So you take a homomorphism to go from one group to another. And for topological spaces, we can take continuous maps. So all these names of these morphisms are just fancy names that talk about the same thing, going from one object to another of the same object. Well, let's think about this in one particular way. Let's take sets, right? Think about a set. You start with an element, and that element belongs to a larger set, right? An element belongs to a set. But what if you could go one step above? What if you could go meta? What if you could take a set and be like, oh, wait, this belongs to something even larger? What if you take all sets? Well, this collection of all sets, we call this the category of sets. And so in general, a category is just a collection of objects that are related to each other with morphisms. You can relate them by going from one object to another object. Here are some examples that we just covered. A set, that's the category. The objects are sets, morphisms are functions. Vect K is a notation for vector spaces. The objects are vector spaces, the morphisms are linear maps. GRP is a category for groups. The morphisms are homomorphisms. Top is our object. The objects for top are topological spaces, and the morphisms, the maps, are continuous maps. A really interesting thing is you can actually go from one category to another. So you can take one of these categories and go to another category. Here's an example. Let's start with a group. Let's take a group. Take like the dihedral group, or sorry, I haven't defined the dihedral group. Let's take the symmetries of the triangle. What we can do is, well, a group is just a set, right? A set with like certain properties. They represent symmetries. You can combine two things, blah, blah, blah. They have an operation. What if we just take the group, forget everything about all these other properties, and just think of it as a set, as just a set with a bunch of elements? For example, like this. We take D6, the symmetries of a triangle, and just think about it as 6 elements in a set. No operations, nothing. This we call, it basically forgets all the properties and turns a group into a set. So we call this forgetful. Another example we just saw is our fundamental group, pi1. Pi1 takes a topological space from top and turns it into a group. And well, this we call, the fundamental group, right? These maps that go from one category to another, we call them functors, which is a really nice name. I like saying the name functor because it's fun, functor. Yeah, okay, anyways. So here's our final step. Here's the final step. We can go double meta. So here are all the categories we talked about so far. But what we can do is, well, we have a way of going from one category to another category. So what if we talk about the category of categories? This is not precise because I should say I should put specifier for the categories, but in general, this is the category of categories. And so the category is called cat, the objects are categories. And to go from one category to another, you can just take functors. So this is category theory, is just the study of these categories. Okay, I don't know how much time I have left.
So,
I have a few remarks on
I think we're a bit over time right now.
Oh, okay, yeah. I don't have much else. This is just Y math, and then, yeah.
Okay, so you want to briefly go through the 3 questions and answer them, or?
Oh, sure. Yeah. Maybe I should stop sharing. Q&A. Oh yeah, so yeah, I had a lot of trouble visualizing. This is answering Richard's question. I had a lot of trouble answering complex analysis questions because it's hard to talk about, 2-dimensionals, because you have to talk about these in 4 dimensions, basically, if you go from 2 dimensions to 2 dimensions. So I think it's kind of, you can either talk about it by, just mapping what happens in 2 dimensions and forgetting about the domain, or you can just not think about them visually and just think about them as functions. Yeah, it's really difficult. I could not get my head around them in the beginning, but good question. The anonymous attendee, I'm not sure. I don't know how I would share the slides, but I will consider it. Final question, Riemann zeta function in a working. I am not sure. I don't know enough about differential geometry, but yeah.
Okay. Thank you so much, Hahn, for the really good talk. And yeah, so you guys are free to go to your next class. Again, it's link.hmmt.org/catalog for the classes. And yeah, hope you have a great rest of your day. And thank you again to Hahn.
Thanks so much.